All right, hello, ladies and gentlemen. Today we're looking at function notation and function operations. Really understanding function notation is the primary goal. And you've got a Delta math assignment to do today. So functions and their graphs. So first we want to do a little bit with domain and range. First of all, we've got some basic functions, and we're going to pay particular attention to domain and range. These are some of the lesser known common functions. Here we have the square root function, which I always call the square root swoop, because the graph kind of looks like the square root symbol. And if you look at the graph, which I always recommend, when in doubt, graph it out. So you could absolutely plug this into your calculator and look at the graph. But what we notice is that domain refers to the x-axis, the x values that work. And so when we're thinking about domain, if you're ever unsure, look at the graph. The graph can tell us a whole lot about the domain. Range refers to the y-axis. And again, it can be very helpful to look at a picture. So for the x-axis for this first function, we see it has an initial point here, which occurs at 0 on the x-axis. And then the graph goes forever to the right. That's what that arrow means. It's going to the right forever. And so that tells us about the domain. The domain starts at 0 and goes forever to the right. At 0, we are going to use a bracket because there's a nice solid initial point there. And infinity uses a parenthesis because we can never actually equal infinity. So because we can't equal it, we use a parenthesis. And then for the range refers to the y values or the outputs. And so we look to the y-axis. So again, our point here, our lowest point, is 0 on the y-axis. And this arrow, not only does it go to the right, but it's also growing upward as well. And so you can imagine that if you look far enough to the right forever and ever and ever, this graph is going up and up and up and up and up. It's going very slowly, but it'll get there. Eventually, it'll go forever upward, forever to infinity in the y direction. So the range is also from 0 to positive infinity. This graph is one I introduced on the first day, and I'm just refreshing your brain. I want you to remember that we have absolute value here. And so what that means is that this numerator is going to be always positive. But this denominator, depending on what your x value is, might be negative or positive. If x is negative 2, then positive divided by negative is going to give us a negative result. So the other thing we want to notice is that these two things are nearly identical. The only thing they differ by is the sign, possibly. And so for the graph for this, if they are identical, it would reduce to 1. Well, they're going to be identical when our x values are positive. We would have a positive 4 over positive 4. That's going to be positive 1. So everything to the right here has an output of 1. When our x values are positive numbers. When our x values are negative numbers, like negative 2, we would get a positive 2 over negative 2, and that would have a negative 1 result. So everything for x values that are to the left, for negative x values, we get a negative 1 result. What happens at 0? Well, at 0, our graphs are undefined. I'm using an open circle here because denominator domain, that denominator can never equal 0. We're not allowed to use 0 as a number we can plug in for x. It's undefined. When the 0 is under, it's undefined. So it turns out for this graph, the domain goes from, this goes forever, all the way out here to negative infinity. And then it comes to 0 right here, and we can't include 0. So our domain goes from negative infinity to 0, and I cannot include 0. I like to do it this way on the axis. Negative infinity all the way over here to 0. That parenthesis means that we're getting very, very close to 0, as close as we want. Infinitesimally close, very, very small. But we cannot include 0. It's undefined there. And it's going to pick up on the other side. So we're going to join these together, 0 all the way to the right to positive infinity. And you do not have to use the positive. It's always assumed there's a positive. I just like to write it in for clarity's sake. And here's an interesting thing. The range for this particular function, the range, what are the y outputs? What are your possible y values for this? It's only -1 and 1. This is called set notation. It's curly brackets, and these are the only answers. So sometimes they might write it like this: x values, this little bar means such that x is equal to -1, 1. This is very old school set notation, so I don't use it very often. But these are the outputs. You can only get a 1 or a -1. All right, let's talk about here. F of x is 1 over x. This is the reciprocal function or inverse function. And again, you can, if you didn't know what it looked like, you could plug this into your calculator. When in doubt, graph it out. And it's this little funky L's. All right. And hopefully you've seen graphs like this before. And first of all, when we talk about domain, denominator domain, that denominator is not allowed to be 0. There is a vertical asymptote. X cannot equal 0. Anytime we have a denominator, it's not allowed to equal 0. The other thing is you'll notice these arrows are getting, as we move to the left, it's getting very, very close to the x-axis. And as we move to the right, our graph is getting closer and closer to the x-axis. And that is because this graph also has a horizontal asymptote at y equals 0. We're going to get close to that horizontal asymptote, but we're not going to touch it. And that really just comes from experience, I think. There is a way to show that, but I'm not going to do that at this time. The domain is x cannot equal 0. You can write it that way. You could have done that here as well. So we could have said x cannot equal 0. Lots of options here. You'll have to look and see what Delta Math wants you to use. You can click view an example, I think, to see how they want you to write your answer. The range for this is y cannot equal 0. Or we could, this is the best way to do it. One thing to exclude. Okay, let's talk about these. These are more complicated. Again, if you ever want to see domain, I'm going to suggest, when in doubt, graph it out. Because especially these are way more complicated. But let's look at this first one. First of all, I see a fraction. Denominator domain, denominator domain. That denominator cannot equal 0. And that's an equation we can solve pretty easily. X squared cannot equal 4. And then I can go ahead and take a square root of both sides. Don't forget the plus or minus. So x cannot equal plus or minus 2. That is the domain for this function. Graphically, I'm going to use my Casio today. I'm going to go to the menu. I'm going to go to graph. I'm going to delete the existing equations. And I'm going to go ahead and type in. Now remember, when you're using your calculator, you need to put parentheses around the numerator and denominator. I only have one term in the numerator, so I don't need it. 1 divided by the group x squared minus 4, close parentheses. Then I'm going to go ahead and execute and then draw. Crazy graph. This is a horrible viewing window. Let me try zoom. I'm going to do shift zoom and see if I can zoom in or maybe auto. Let's see what auto does. Well, it's a little better. So you have to know what your graph is doing. Are these like vertical lines really there? No, they're not. It's just a terrible picture. And you really need to know when it's a terrible picture. So what's really happening? From the denominator, we're always going to get vertical asymptotes. That's what VA stands for, vertical asymptotes. So at -2 and +2, we get these vertical asymptotes. And then in between, it looks like our graph is approaching this horizontal. There's a horizontal asymptote as well, it appears. And what happens is you see there's like 6 different sections here, and we usually fill up about half of them. So we've got an L in this upper left corner. It looks like we have a parabola shape going on in the middle here. And it looks like we have another L on the right-hand side. So this is a better graph. This graph does have symmetry. This is symmetry with respect to the y-axis. And if you wanted to prove that to yourself, you could pick a few points and see that it has that even symmetry. All right, let's look at this one. This is very interesting. When you have a fraction, denominators are not allowed to be 0. That's a good thing to write down. Denominators cannot equal 0. And that's a great thing for you to solve. It just gives you the exclusions from the domain. This is a square root function. And like this one, you'll notice there's no picture to the left-hand side. And there's no picture because I cannot take the square root of a negative number. I cannot take the square root of -25. It is imaginary, meaning it's imaginary. There's nothing really there to show us. We can only see a picture when there are actual real outputs, not imaginary things, but real things. And so let's look at this graph and see if we can't figure out what's happening. Because again, when in doubt, graph it out. I'm going to press exit, and that'll take me back to my menu. Delete, yes. And I'm going to type in square root. Again, I need to tell it everything needs to be under that radical, so I need to use parentheses. X squared plus 3x, whoops, delete, x, there we go, -4. And I want to draw that as well. Oh, very interesting. What a weird graph. So let's see if we can figure out what's going on. It looks like my graph sort of picks up in the middle of nowhere. That's kind of odd, but it looks like it's happening about at 1. And it looks like it's going off like that. Over here we have -1, -2, -3, -4. So 1, 2, 3, -4. And again, it looks like it's picking up from nowhere. It does look, like, I don't know, like antlers, antenna? Who knows? Kind of bizarre, but it does look like it's going off to the left and this side's going off to the right. Let's see what's happening. It turns out that when we have a square root function, for square root functions, everything inside that radical must be greater than or equal to 0. Why must it be greater than or equal to 0? Because if it was less than 0, it's imaginary. All right? So right off the bat, because it's a square root function, whatever is inside has to be positive by default in order for us to have a picture. Well, I can solve that equation as well. I'm going to square both sides. The square root and the square cancel out. So I have x squared plus 3x minus 4 is greater than or equal to 0. Well, this is another interesting thing. This is a quadratic inequality. If it was linear, if it was x to the first, it'd be easy to solve. Quadratics are much harder. This graph is factorable. Let me do that first. So always, we want to be able possibly to solve, I can't really solve this inequality. Instead, I can solve the equation. Where does it equal 0? So I can double bubble this. I can factor. X times x is x squared. What times what is -4? +4 and -1. And when I check that little rainbow, check the smile, or the rainbow, whatever you call it, -1x, +4x, that gives me my middle term. So we're able to figure out where it equals 0. It equals 0 when x is -4. Hey, that's very interesting. It's equal to 0 when x is equal to -4 and when x is equal to 1. So it actually has a value of 0. So those are actual ordered pairs on this graph. Now, what's going on with this picture? This is kind of weird. This inequality has a graph. So I can sketch this pretty easily. I know it has a 0 at 4 and a 0 at 1. It's also a parabola. It's an up parabola. And it's asking, where is this parabola greater than or equal to 0? Where does it have values that are greater than or equal to 0? Well, all of this section of the graph has y values that are greater than 0. All of these x values from -infinity to -4 are either 0 or above. And all of these values from 1 all the way to the right, all the way to positive infinity, also have outputs greater than 0. Our graph is positive to the left of -4 and positive to the right of 1. In between -4 and 1, our graph has a negative value. It's less than 0. And we're interested in where is it positive. Okay, so everything, which is how this comes, it's actually connected. And again, your calculator just couldn't actually draw the whole thing in. So this graph actually does look like this. So what's the domain? What values of x can we actually use? This domain is, you can see in the picture, -infinity all the way to -4. Parenthesis at -infinity. Why do we use a bracket at -4? Because that's where it is actually equal to 0. So that whole thing equals 0 at -4 and 1. So we can solve equal to 0 very easily. And from 1 all the way to positive infinity, we also have an output. All right, so these are very complicated, but using the graph can be very, very helpful. Our graph appears from everywhere to the left all the way to -4. It picks back up at 1 and then progresses all the way to the right. All right, so using a graph can be very, 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 very helpful. And these are quite tricky, so pay attention to those. Let's try some other stuff. I only get 30 minutes on this recording, so I'm going to maybe pause and ask you to pause and answer them, fill them out, etc., to kind of speed things along. Example 1, again, you're going to write the directions. Evaluate given f of x is equal to x minus 3 and g of x is x squared minus 4x plus 3. We want to state the domain. For each of these, just to get started, f of x here, this is a line. If we were to graph it, it looks something like this. It's got a y-intercept of -3. The domain for this is all real numbers, -infinity to positive infinity. The second graph here is x squared. We know that that's a parabola shape, and that's great. It goes forever to the left and forever to the right. So that is its domain, -infinity to positive infinity. These are polynomials. Polynomials always have domains of negative to positive infinity. They're continuous curves that go on forever to the left and forever to the right. They get all of those horizontal x values. Here we have function notation. F of g of x, f plus g of x is how that's read. And we want to, what it really means is, this is notation. You need to know this. F plus g of x really means take your f of x function and add your g of x function. Very easy to do. Our f of x function is x minus 3. our g of x function is this whole thing. And so we simply need to combine like terms. So we have x minus 3 plus x squared minus 4x plus 3. And then we just need to combine like terms. 1x squared, 1x minus 4x is negative 3x, and then positive 3 and negative 3 is 0. So this is f plus g of x, right there. And the domain, again, this domain is a parabola. Its domain is negative infinity to positive infinity. When in doubt, graph it out. You're welcome to graph that and see that it just goes forever to the left and forever to the right. Well, that's how I think about domain. How far left and how far right does it go? So I'd like you guys to take a minute and see if you can figure out these. So pause the video, work out B, C, and D, and then I will pop back in and explain some things. Okay, so hopefully you worked that out. Again, all of this is notation that you probably learned, hopefully learned, you should have learned last year. We did it. So key mistakes here. Distributing the negative. Did you distribute the negative properly to combine like terms? Over here, this is multiplication. You're just multiplying and combining like terms. That's not hard. But here we have a fraction. And anytime you have a fraction, you're going to have domain issues. Denominator, domain, denominator, domain. So sometimes your f over g just stays like this. But you want to factor if you can. And it might be possible to reduce. So you always want to reduce if you can. That's a big part of what you're going to see coming up in calculus. So if it looks easy to factor, try, factor it. When things are factored, it's very easy to see what's excluded from the domain. And that you can see right here. And this is the simplified result. All right. Let's try some composition. So here is composition of functions. Example 2, evaluate given f and g. So composition is a little more challenging and something you want to pay attention to. And I like to think about it as an outside function and an inside function. And first of all, this notation is terrible. I hate it. F, this is read of g. And then in here is another of. So f of g of x is how we read that, and it's awful. What it really means is, I'm going to write it in red, f is on the outside, and g of x is this little inside piece. So again, I'm going to color code. Here's g of x is blue, and we're going to call f of x is the red function. So what I'm going to do is I'm going to do this in a couple of steps so you can see how to do this in terms of x is what that means. In terms of x means you're going to have x's in your answer. And so here we have g of x is on the inside. When we do order of operations, we always work from the inside out. So what can I replace g of x with? Well, g of x is equal to x squared plus 1. So I'm going to put in substitute g of x in place of, we're plugging in x squared plus 1. They are equal to each other, so I can replace them. And now this is saying go to your f function. So there it is. There's our f function, and you're going to substitute in this x squared plus 1. So in place of x, substitute the whole x squared plus 1. All right. And so this literally, it's a placeholder. The f's match. And then here, in place where there was an x, you're putting in this stuff now. So everywhere in this equation, you're putting in x squared plus 1. So the f function had a 2 and then an x and a minus 3. And in place of the x, we put in that x squared plus 1. You're going to see a lot of this. You have a timed little thing to show you the substitution, just like this. This is a great thing. And from here, you can just simplify. So we're going to go ahead and distribute the 2. So 2x squared plus 2 minus 3. And we get 2x squared minus 1. And that is f of, whoops, not f of f, f of g. And that's just the simple notation there. You're allowed to write that. F of g is 2x squared minus 1. Over here, this is g of f of 2. So this is numeric. It wants you to put in a number instead of just using x's. So we're going to do that pretty much the same way. And I'm going to start with rewriting this notation because I don't like it. So it's g of, and then on the inside, we have f of 2. So it kind of goes in order. And we're going to start with this inside piece. What does f of 2 tell you to do? It says go to the f function, and what are we doing? We're plugging in a 2 instead of x. Replace x with a 2. That's what that means. I am going to run out of time. All right, that's a bummer. We have g of, and we're just working from inside out. So I'm going to go to my f function, and I'm going to plug in a 2. So that is 2, and in place of the x, we put in a 2. There we go. Can I figure this out? Yes, I can. G of 2 times 2 is 4, minus 3 is 1. And so now this is saying go to your g function. Boop. In place of the x, we're plugging in a 1. So there's my g function. And in place of the x, we're plugging in a 1. I'm going to just write my function something squared plus 1. And we're plugging in place of the x, we're putting in a 1. 1 squared plus 1 is 2. That is g of f of 2. So when they plug in numbers, they want a number answer. But if it says of x, then your answer should have x's in it. All right, example 3, we're going to use the graph to help us. This is a generic graph. You can see this is the graph F, and here we have the dotted graph G. And I'd like you to give these a try and see if you can figure them out. I will talk you through the first one and see if you can go from there. So first, I'm going to rewrite this icky notation. I'm going to say f of g of 3. And they want us to start on the inside. So I'm going to look. G of 3, go to my G graph, and that is go to where the x is 3. So here's where x is 3, and it's asking what is the function output. The x is 3. What's the output value? Well, it looks like the output value is right here at -1. So I think that's -1. And so now it's saying what's f of -1? So that says go to the f function. There's the f function. Where x is -1, here's where x is -1. They want to know what is the output. If the x is -1, what's the output? Right here is 4. All right, take a moment and try. Okay, so hopefully you were able to go through those pretty easily. And again, look at my arrows. This is saying I'm starting on the inside and I'm going to F where the X value is 2. The output has an output of 1. So that's what that arrow means. And then it says go to the G function, my dotted function. When X is 1, the output is -2. You can see here it's asking F of -5. Well, F doesn't go to -5. That is, 5 is not in the domain. -5 rather is, oh, I did that backwards. Here, G of -5. G doesn't go to -5. It's not in the domain of G, so it's undefined. There's nothing there. There's no defined point there. The same thing happens with F. Please let me know if you have any questions with these. Again, pause the video and write this stuff down. Make note of any questions and let me know during class. But otherwise, that is it, ladies and gentlemen. You can go do Delta Math Calc 0.9.